Hello there, chemistry student. Today we're going to talk about heating and cooling curves. First, I'd like to start with a review question. Hopefully you remember how to do this with the Q equals mcat equation. I'd like you to calculate the final temperature if you add 6,000 calories to 10 grams of water at 90 degrees Celsius. Okay, well, let me help you out with this. We'll speed this along so we can get to the new stuff. First, you would use basically the Q, heat equals m times C times delta T equation. Plug in the numbers that you're given. Solve for delta T and find out that the temperature is going to change by 600 degrees Celsius, which would give us a final temperature of 690 degrees Celsius. Now that has sig figs, that has units, that looks good, right? Now, hold on a second. You should always check your answer to make sure it's reasonable. Is that a reasonable temperature for water to exist at? That's a pretty high temperature. In Fahrenheit, that's 1,274 degrees Fahrenheit. That's pretty darn high. Do you think water is still water at that temperature? No, it is not. Water will evaporate at 100 degrees Celsius, at 212 Fahrenheit. So we are way above the vaporization point of water. So we can't just use this equation if we're going to take water or any substance outside of the region at which it exists in that phase. Let me give you an example of this. So let's take this solid here. Oh, nice sound effects. And we are going to add heat. It's on a Bunsen burner. And we're going to add heat as it melts. And you can see that as time goes on and we add heat, its temperature goes up and up and up. And eventually, it starts to vaporize and its temperature levels off for a little bit. This is the vaporization point that we're at. And we see that it melted initially at the beginning at 0 degrees Celsius, and it boils here at 100 degrees Celsius. That's very similar to what water does. Here's what's happening at the atomic level. At temperatures below 0 degrees Celsius, you see that we have a solid. When you get to 0, the melting point for water, you see that ice and water coexist. It doesn't all just immediately turn into water. It takes a while for all of the ice to get enough heat to turn from solid to liquid phase. Then as we heat it from 0 to 100 degrees Celsius, we have pure liquid. But once you get to 100, it'll take a little bit more heat to vaporize all of those gas particles. And finally, when the temperature gets to be above 100, you will have a complete sample of gas. This diagram here is called a heating-cooling curve, or you might also hear it called a phase change diagram. And this illustrates the temperatures at which any substance will exist in different states of matter. And it shows how, as we add heat, the temperature changes. Now, we're going to work primarily with a diagram for water like this, but other ones do exist. There's some examples here. Notice that this one, which is for iron, has a melting point of 1,500 and a boiling point of about 2,750. So much different than water's, but the same general idea. You'll want to draw a diagram like this in your notes. Make sure that you label all of the words and temperatures that you see here. Notice that we have solids, liquids, and gases, and each of the phase changes is labeled here. Going from a liquid to a gas is called vaporization and happens at 100 degrees Celsius. The opposite process is called condensation, also happening at 100 degrees Celsius. Usually we call solid turning into liquid melting, but we're going to call it in this unit fusion, and that's going to come into play later. And the opposite process is solidification. If we are adding heat along our x-axis, we are going up on the graph. The temperature will rise as we turn a solid into a gas and add heat. The opposite process, removing heat, is exothermic. And if you remember from our earlier discussion, anything that is endothermic will have a positive Q or heat value. Anything that's exothermic has a negative heat value. And here are the equations that we're going to use to calculate that amount of heat in each region of the graph. I want you to first notice the Q equation for liquid water. Notice that Q is m times C times delta T, and C is 1. That should look really familiar to you. That's the region we've been working with so far. Also notice that for gases, for the gas phase, we use the same equation, but now the C value, the specific heat value for a gas or a vapor, is smaller, 0.4. That means gases change their temperature with less heat added. Same thing for solids. They're still using the MCAT equation, but the specific heat value is 0.5. You do want to memorize this 0.5, 1, and 0.4 value. Now let's talk about this flat region of the graph. As you saw in our little animation, as you add heat, at 100 degrees Celsius for water, the temperature doesn't change. So we can't use the MCAT equation because there's no delta T. The temperature is not changing. The equation that we're going to use is to take the mass and multiply it by the heat of vaporization, the delta H VAP. And for water, that value is 540 calories per gram. And that'll tell us how much energy it takes to melt or vaporize, depending on whether we're talking about the blue or the orange region, to melt or vaporize that substance. If we are melting, the delta H value for fusion is 80 calories per gram. Again, you'll want to memorize that 540 and 80 value, but I think you're going to use it enough that it will become second nature for you. Let's do a sample calculation together. I've sketched a diagram of our heating cooling curve up in the upper right hand corner here. We're going to label where we're starting and ending on that diagram. We're going to figure out how much energy, how much Q, is required to turn 52 grams of steam starting at 123 degrees Celsius, so that's up here above 100, to turn it into liquid water at 80 degrees. 80 degrees is about here, and here's our liquid water. So notice that our graph is discontinuous. We can't calculate how much energy it takes to go directly from this point to this point. We have to go through 3 steps. First, we're going to take the steam and cool it down to 100 degrees Celsius. Once all the steam is at 100 degrees Celsius, it will condense into liquid water. And then once we have all the particles as liquid water, then they will cool down from 100 to 80. So there's 3 steps. And our total Q value is going to be the sum of each of those 3 partial Q values. Also note that we are going down our graph. So this is an exothermic reaction, or an exothermic process. So our Q values will end up being negative. Let's write down the 3 equations we're going to need to use to find the Q, the heat, for each portion of our phase change. These equations are the same as what you saw on that other diagram, but I have filled in the delta T. Now this is something that confuses a lot of students. You're not changing the temperature from 123 to 80 all in one step. In our first step, we were only going from 123 to 100. So our delta T here is just going to be 23. For Q3, our temperature started at 100 and goes down to 80. So our delta T is just 20 there. So let's plug in the numbers that we are given. The mass in each of these cases is 52 grams. So 52 times 0.4 times 23. And the mass of 52 times 540 will be our Q4. And for our final one, we have 52 times 1 times 20. Now, I haven't been very careful with my signs here. We did say that these would all be negative. Each step is going to be negative. You know, technically our delta T here is negative 23. Technically here we should make our delta H negative 540, and our delta T in our third step should be negative 20. So take a minute, multiply all those out. Hopefully you got the same numbers here for Q5, 4, and 3. And now what we're going to do is just add up all of those numbers. Now, I do want to point out that the Q4 is a pretty large number, and you'll always see that be the case. It takes a lot of energy to vaporize or condense any amount of water. When we add these up in our calculator, we should get negative 29,598.4, and our unit is going to be calories. These units will always be in calories because these numbers are based on calories. Now, I have some really good news for you. You do not have to do significant figures with these calculations. Yay! It would just be a little too complicated, so we're just going to simplify it and say you can record the number exactly as you get when you add it up. Now, it's never wrong to do sig figs, and if you'd like to know how to do that, please talk to your teacher. Okay, let's go back to our original problem and see if we can figure out exactly what the final temperature would be if we did add 6,000 calories to 10 grams of water at 90 degrees Celsius, if it's not going to be 690. Here's what we are going to do. This is kind of a tricky one because we don't know what temperature we're going to end up at, but we know where we're starting. We're starting at 90 degrees Celsius, so somewhere in here, and we're adding heat. So We have enough energy to take all of our liquid up to 100, and then we have enough energy to turn all of our liquid into steam. Let's see if that's the case. So we'll find Q3 and Q4. Q3 is mass times C times delta T, and it's going to take 10 degrees Celsius to go from 90 up to the boiling point of 100. So that would take only 100 calories. We have more than enough to do that because we have 6,000 calories. So let's see how much Q4 would take. Q4 is going to be the mass times 540. That would be 5,400 calories. Okay, so both these steps together are only 5,500 calories, so we still have a little bit more to spend. At this point, I would probably say, okay, let's figure out how much we have left after we've done those two steps. We've used, of our 6,000 calories, we've used 5,500 of them. So we have 500 calories left. And we want to find the final temperature. So let's see how far up our temperature can go in our gas phase. If we're going to use all 500 calories, oops, I should probably write our equation down. We have Q5 equals M times C times delta T. And we know that we're going to use 500 calories for that. The mass, we said, was 10. The specific heat at this temperature is 0.4. And we're going to find how much our temperature will change. So let's see. 500 equals 4 times what we're solving for. So 500 divided by 4 should turn out to be a delta T of 125 degrees Celsius. Now, what temperature were we starting at? We initially started at 90, but in this step, we were already at 100 when we started calculating our Q5. So our temperature is going to increase from 100 up 125 degrees, so we should end at 225 degrees Celsius, which is much more reasonable than 690 degrees Celsius. Okay, we got one final problem here. This one is for you to try and bring to class with you. The question is, how much energy does it take to convert 20 grams of water at 15 degrees Celsius to steam at 100 degrees Celsius? So figure out where you're starting and ending on your graph. Figure out which steps you're going to need to add together and calculate the number of calories it will take to do this entire process. Again, remember to include units. Make sure that you don't have to do sig figs, so don't worry about sig figs. Bring that to class and we will check it together.